All right, so there's our first question. So I'm just going to crank through. If you have particular ones, you've been looking at the practice exam and you're like, hey, I really want to see number 7 on part 2, just let me know and we can go there.
Part 2.
No, I was just kidding, Thea. I'm not going to really do what you want. No, I'm kidding. Yeah, kidding about kidding. All right, so I will do it if you got a particular one. All right, so let's go to this one. This one is, this is a tricky one. So what does it say? Find the function that is finally graphed after the following things are done. All right, so they start with y equals the absolute value of x. And then what do they say to do? They say write 3 units. So the first step is move the thing right 3 units. So what happens when you move it right 3 units? Yeah, good. So that's the minus 3 in there. That's right 3, huh? Because x does the opposite, so it's minus instead of plus. X is always the opposite of what you would naturally expect. And it's in there, right? Any x thing is in the whatever, in the absolute values. In other words, it's not like this. It's not, the minus 3 is not outside the absolute. That'd be a y. That'd be a down 3, wouldn't it? Right? If it's an x, it's in the absolute values or in the square root or in the whatever, you know? All right, next step. Stretched vertically by a factor of 3. So stretching it up. Got to make that sound. So what's going to do that? That vertical stretch of 3. It's going to multiply the outside by 3. Vertical stretch of 3. Am I on the screen? Yeah. Make sense? Multiplies by 3 on the front. Notice it's not like inside the absolute values. It's not like that. Why not? Because it's not an x. It's a y. Vertical things are y. Remember, the y world is outside of the absolute values, and the x world is inside of the absolute values, right? Or the whatever. If we had the square root graph or the cube power. Yeah.
So that's why you
Tim.
use terminology for stretch vertically or stretch horizontally, so you know whether to put it outside or inside.
That's it. Vertically is up and down. It's y. Horizontally is right and left. It's x. Absolutely. That good? Are we happy? Let's keep going. Shifted vertically down 2 units. Down 2. What's going to do that? You know that. Just put a minus 2 out there. That's down 2. Right? That's what'll do that. We good? Okay, now here comes the real tricky one. Reflected across the x-axis. X-axis. Well, first off, you have the x-axis. If the x-axis, reflection is mirror talk, right? You reflect in a mirror. So we're reflecting across the x-axis. So that'd be like if you're up here, you go down there. Well, it's supposed to be lined up, but you get the idea, right? So that's a reflection across the x-axis. The x-axis is a mirror. So if you reflect across the x-axis, that's a vertical reflection. So that's like reverse of what you would think. You don't think x-axis, you would think sideways, but actually, if the x-axis is your mirror and you're reflecting across it, that's a vertical reflection, isn't it? It's an up-down, it's a y kind of thing. Remember how they trick us with that? So it's a vertical reflection, it's an up-down reflection. So I'm going to do something in the y world, aren't I? You with me? Because it's really a vertical effect, an up-down y effect at the end of the day, even though it's mentioning the x-axis, right? Okay, so what am I going to do in the y world? What's going to make a reflection go up-down? A negative on all of y. Right? Now, if it was an x, if it was a right-left reflection, then I would just I would replace x with negative x, wouldn't I? If it was a right-left kind of, if it was reflection across the y-axis, a right-left reflection, I would stick negative x in for x, wouldn't I? But it's a y, vertical, so what am I going to do? I'm going to stick negative y, where's my pen? There it is, negative y in for y. Now, I know that I probably haven't mentioned it this way before, but I think this will be easier. Let me bring it over here. Negative y in for y. Oops, I wrote the wrong thing. Okay, you guys with me? What did I do? I just stuck a negative y in there because it's a up-down reflection, right? It's multiplied by negative 1 is what makes something do that. Now, that is the right answer. I'm fine with that. If you give me that on a test, but it's multiple choice. So I got to figure out which one of these it is, you know? So none of them look like this. None of them have a negative y. They all have a regular y. So I've got to make mine, even though mine's right, I got to make it look like theirs so I know which one to grab, right? So how am I going to make mine look like theirs? Well, you don't want that negative on the y. So what am I going to do to make mine look like theirs? Yeah, divide through or multiply through by -1. So let's do that. Let's multiply through by negative. So I'm going to multiply this side by -1 and that side. The two negatives cancel, you get regular y. And I'm just going to stick the -1 in the front. Could you distribute it? Sure. But I'm looking at the answers and they did not distribute them. And I'm trying to grab the right one. So which one looks like that now? C. No, not that it's not okay to distribute the negative. You could distribute the negative, but I'm just trying to make mine look like theirs so I know which one to grab. Negative in the front, and then 3, absolute value of x minus 3 minus 2. That's C. That's what they have on C. So C is the answer. Is that good? Questions? Okay. So here, I'll get both of them, 5 and 6. So remember what you do on these kind. This is not piecewise. That other one I just skipped, number whatever it was, 4, was piecewise because it had several different functions, right, that existed in different places, right? Maybe I should go back and set that one up. But anyway, let's do this one for now. This is not piecewise. These are not. These are just one function, one function. You guys getting what I'm meaning on the difference between this and the piecewise? The piece has several pieces, right? This does not. This is one function. Boom. This is one function. Boom. Not pieces. All right. Right? Doesn't have, x between here and there. Doesn't have any of that. Right? All right. So how do we do these? Well, central point, one other point. So make an xy table and then find the central point. Okay, where is the center, always going to be? How do you find the center? Remember the trick for finding the central point? Make the x world equal 0. Make x's little world become 0, right? So make the x zone become 0 at the center. So so you look at the function, what is it? It's y equals negative parenthesis x plus 2 cubed. So here's x's little world, the parentheses, right? When I say x's zone, I mean the parentheses or the square root or the absolute value, the little zone inside, right? So what's going to make that little world become 0? -2. X -2 is going to make the parentheses become 0, right? So that's where the center is. Plug that in. What does y become? Negative. Negative's on the outside, huh? Doesn't really matter, but this one. -0 cubed, which is better known as just 0. So 0. -2. So that means back 2, up 0, right there. That's where the center has gone. All these graphs, the 6 basic graphs, right, you're going to have on your 3x5 card for tomorrow, right? Those 6 basic graphs, absolute value and all the rest, those are all centered at the origin, originally. But then they're moved. This one's moved left 2 units. Okay, now, find one other point. How do we find the one other point? Just add 1. That almost always works. I say almost. It won't work on number 6, and we'll see that in a minute. So add 1. That'd be -1. Plug in -1. What do we got here? -1 plus 2 cubed. What is that? -1 cubed. -1. Back 1, down 1. Right there. Back 1, down 1. See on the graph? So I got my 2 dots. Now, we have to also generally know what is a third power graph. What is y equals x cubed, which is what it basically is, right? What does that look like? That's the snake, right? He snakes up and down. So this is the center. Let him be the middle. So and then it must go this way. So then it must also go like that, right? It snakes. So there it is. Right? Bold turned up, bold turned down. Remember, the power graphs go up and down fast, don't they? In other words, don't make your graph go like this. That would also go through the 2 dots, but it would be wrong concavity, wrong bowl turning, right? Good there? Everybody happy with that? Does that make you happy? All right, let's go to number 6. Right here, same kind of thing. X, Y. We got to find the center. How do we find the center? What's going to zero out X's little world? What is y? Y equals the square root of minus x plus 2 minus 3 on that side. So here's, whoops, I just bumped the crazy thing. So here's x's little world right there, huh? In this case, there's not parentheses, but there's a square root. So that's x's little world. What's going to make that little world become 0? Going to plug in x regular 2, huh? Positive 2, regular 2. Exactly. Plug that in. Y equals the square root of negative 2 plus 2 minus 3, which is 0 minus 3, which is negative 3. That's where the center has gone. Over 2, down 3, right here. That's the center. Over 2, down 3. Does that make sense? We're always finding where the new center has gone. That's the most important point on the graph, isn't it? The center. Okay. So we got that one. Now, how do we find our one other point? Well, usually, we just take whatever we got for the center and we add 1. This is the one time it won't work. Right? When we add 1, it's going to tell us no. Right? Let's plug that in. Negative 1 plus 2 minus 3. That's the root. Wait a minute. I didn't add 1. What am I doing? I'm thinking, this is working. What's going wrong? Yeah, I subtracted 1, which is what will work, but we're not doing that now. It's supposed to be 3. Just tell me when I do things like that. So that's 3. I'm supposed to add 1. That's 3. Let's try it again. Now it won't work. Plug it in. Negative 3 plus 2. What's that? Root of negative 1. That's no. Can't have the root of a negative. That's imaginary. No. Now that's important information. I'm going to go over here at 3 and write no. At over 3, no. The graph is saying, I don't go that way. Right? I don't go to the right. So you know it's going left, huh? So that's the one time the add 1 thing won't work. So when that happens, instead of adding 1, you subtract 1. So plug in 1 from the original. It's all compared to that original center, which was 2. Right? Try adding 1. That didn't work, so subtract 1. Now plug in 1. That'll work. I don't know if I even have room for that. Where am I going to do that? We'll go over here. So that's going to be the, what is it? The square root of negative 1 plus 2 minus 3 on the screen, okay. Root of 1 minus 3, what's that? Negative 2? Did I do that right? Yeah, because that negative 3 is outside the root, huh? So negative 2 over 1, down 2, there it is. There's the other dot, over 1, down 2. So it starts here. This is the center. It's important to know. Because another mistake I see a lot in the exam is people will get confused which one's the center. They'll start at the other one and go down or something. I see that kind of thing. They'll start here and they'll go, oh, it goes this way. Well, they're not starting with the center, right? So be clear which one is the center, so that because that's your starter. So what was the center over 2 down 3? It was here, and over 1 down 2 is here. Yeah, so it must go. Now, is this right like that? I started at the center. I went through the other dot, and I'm dead wrong. Why is that wrong?
Because it's going up, it should be going.
Yeah, remember, root functions are slow growing. Power functions go up and down fast, third power, second power, but root functions don't bowl up, they bowl down, right? They grow slowly, not quickly. So let's try that again. I've done everything wrong you can do, I think. Over 2 down 3, over 1 down 2. Yeah, it goes like this, huh? Slow growth. Slow growth. Bowl turn down. There we go. And that's the only function that doesn't go both ways. He doesn't go to the right at all. Right? The square root function is the firework, right? It's like you set it on the ground and it shoots one way. It doesn't go the other. All right. So good. Questions on that one? Let's see. All right. So I'm going to just start the piecewise, but I'm not going to do the whole thing. All right. I just want to make sure you remember this. I went back to number 4 now. So going back to number 4, this is piecewise. See it? It's in different pieces. Right? It says, hey, you do this in certain regions and do that in another region and do this somewhere else. It's in pieces. Piecewise function. Right? The main thing to remember is to put in the walls. Where do the walls go? -8 and 4. So go over here to -8 and put in a wall. That's at -8. And go over here to 4, +4, and put in a wall. That's at +4. That's where the walls are. That means this graph is going to be in different pieces, right? Now, what is it going to do where? And then right in the top, the functions that it does in those places. It does x plus 3. This is y out here, right? F of x is y. It does x plus 3 when you're between -8 and 4. So in here, it's going to do x plus 3, isn't it? And when you're to the right of 4, it's going to do the -x plus 7 equation. See what that says? It's telling you which equations to do in which locations. That's the whole point of a piecewise. Everybody see that? So I'm writing in the top which function in which sections. So I put the walls in, put the functions up there. And what does it do right at 4? It's at -9. So just do that. At 4, it's right here. Whoops, can't do that very well. Let me change my color. So right there. That's over 4 down 9. It just does exactly that. At over 4, it is at y equals -9. That's a dot. That's a solid dot. Then you make your tables. So make an xy table for the middle section. Make an xy table for the right section. This is going to be y equals x plus 3. Now what are you going to plug into that table? Here I am. I'm doing the whole problem. Huh? All right, real quick. So what are you going to plug into that table? The walls. Always do the walls. Everybody hear me on this? Right? Don't just, here's the common mistake. Here's the common mistake. I'm just saying it. I'm always surprised when people do it, and I think, I said it. It isn't like I didn't say it. I said it straight. So I know a lot of what I say, the 1, 1, 1 might fly over. But do the walls. Don't just do -7. That's a common mistake. Because people go, well, Mr. Heron, well, or they'll go, I'm not going to do 4 because it's less than 4. It's less than 4, so I'm not going to do 4. I'm just going to go to 3. Wrong. Wrong. Why? Because it does do 3.9999999. It basically does 4. So you got to go to 4. Don't just think whole number-ish, right? There's not just 3 and then 4 and nothing in between. No, there's all kind. It basically gets to 4. So you got to do 4, but circle it. Remember me talking about that? You got to get to that wall with an open dot. You can't just go to 3. I see that mistake all the time because there's just whole number thinking. Does that make sense? You got to go to 4, and you got to do -8. I'm not going to circle it. It does hit -8 right in the money, doesn't it? Right? It's the x is equal to the -8, right? That making sense? So, all right, so plug in those two values to this function. What do you get? 4 plus 3, 7, but circle it. So that's over 4 up 7. That's about here. Open dot at over 4 up 7. Plug in -8, get -8 plus 3. What's that? -5. -8, -5. Where's that? About right here. So, boom. Straight line, huh? Solid dot here, open dot there. That good? Just do the two walls over here on the right side. I'm going to do -x plus 7. What am I going to do? I'm going to do the wall. I'm going to do 4, but I'm going to circle it because it says greater than 4. It doesn't mean I'm going to start at 5. Right? 4.0001 is included, so I basically need to do 4 with an open dot. And then just do one other point. Who cares? Like 5, 6, 7, whatever. Plug it in. So you get -4 plus that. It'd be 3. Circle it over 4 up 3. Where's that? Down here, about like there. And over 5 up 2. 5 up 2 like there. Solid dot. Zip, zippity-doo-dah. Off that way it goes. There it is. The piecewise graph. Which I said I wasn't going to. In my mind is my years of teaching and all the ways people don't remember those. And I think, oh, I'll just say it, and then they'll remember. Which might be true, might not be true. So maybe I'll just do it. Remember, you got to get the equation. What's the equation for this little piece? Remember how you do that? How do you find the equation? Y equals mx plus b, because it's a line. It's a straight line. All right. What's the slope there? How do you find the slope? Here, let me put it over on this side since it's, maybe I'll do this one over here. How do you find the slope of this thing? Yeah, either the slope, good, well said. Either the slope formula, or I can't erase this. Either the slope formula, or or just rise and run. I'm just going to go rise, run. Can you tell how far did I go up? Go up 1, 2, 3, 4 over 1, 2, 3. So up 4 over 3. Everybody good with that? I just did rise, run, 4/3. M is 4/3. What's the B? Yeah, B is where it hits the y-axis right there at up 4. So the equation of that piece is 4/3 x plus 4. Okay. What's the equation of the other piece? What's the equation of that? So, well, it's another y equals mx plus b. What's the slope? The slope goes up 2, up 1, 2 over 1, 2, 3, huh? Up 2 over 3, right? Rise over run. That's what slope is. X plus b. And what's the b? The b is the y-intercept, huh? It's where it hits the y-axis. 2/3 x plus, where's it hit the y-axis? Right there at 0. Just 2/3 x, huh? So then when you put the whole thing together, you've got to say, okay, so the y or the f, I don't care if you just write y or f, whatever, is basically, it's the 4/3 x plus 4 function in some places, and it's the other function in other places. Where is it the 4/3 x plus 4 function? Let's go back to the picture if you can see it. Yeah, where does this exist? Well, he exists, I can erase this, he exists from -3 to 0, doesn't he? That's the x territory, right? From -3 to 0. From -3 to 0, this function exists in here, doesn't it? And where does the right function exist? The other one, the 2/3 x plus 0, we don't need that, exists in here. What's that, from 0 to 3? From 0 to 3. Now, I don't know about I can't even tell if there was open dots or so. It's fine with me if you just make them all equal. I don't care. Yeah, they weren't clear in that diagram about open dots or solid dots. I couldn't even tell. So, good enough. If they were more clear, like if that was an open dot, then I wouldn't have it, I would not have this here, right? Anyway, you know about all that. All right, let's go on. How do we solve this one? This is part 1, so you won't have your graphing calculator, so you're going to have to use your algebra skills. How do we, I've noticed that's often, it can be a little rusty for people, so let me help with that. So how do you solve that one? Yeah, get rid of the fractions, huh? Whenever you're trying to solve something with fractions, just get rid of the fractions. What's the LCD on that one? Yeah, 14x. How we come up with the LCD, you just take, the LCD is 7x times 2, 14x, right? And so you multiply 14x, and 14x, top. All three get it, right? So you just multiply the denominators together. 7x times 2 is 14x. That's the LCD. You put it top. You multiply them all by that, and then you cancel. Right here, x cancels x. 7 goes into 14 2 times. 2 times 6 is 12. Out here, it's just 14x times 1. And over here, 2 goes into 14 7 times. It's 7x. Everybody with me? It's getting kind of messy up there. Is that okay? So you see what I did? 14x, 14x, 14x. And then in the middle, I canceled. X is canceled. 7 went into 14 2 times. So you cross-cancel and multiply whatever's left over. 2 times 6 is left over 12. These guys just multiply because there's nothing under a bar to cancel, so they just multiply. And over here, 2 goes into 14 7 times. What's left over? 7 times 1 times x, 7x. So now we're to here. No more fractions. Much nicer, huh? No more fractions. How do we solve that thing? You could, I think I'm going to subtract the 14x. It'll just be a little quicker. So you get minus 12 is minus 7x. Divide by the minus 7. There we go. So it's positive 12 sevenths. So we got it. Good on that? So I don't know. Whatever that practice exam has. 20. I think it's 20 or 25, something like that. Okay. So there's a world of difference between absolute value less and absolute value greater. You want to have that in your 3x5 card, right? So for absolute value less, for the less case, see how this one is greater case? So for the less case, what do? You put the -7 in the positives. Yeah, we're always removing the absolute values. And you keep both symbols less. That makes sense? And then you just solve it from there. The other one's greater. This is the greater case. Oh, the first time you got to get rid of that too, huh? We always have to do that first. If there's something outside of the absolute values. We good to there? So now, now you go to removal. So what you get the absolute values alone, and then you go to removal. So first, get absolute alone, then remove. So how do we remove? What do you do for greater? You're going to have less than -7 or greater than +7. And I'm running out of room there. Let me squeeze that in again. So you're going to have, again, two separate statements. Less than -7 or greater than +7. Everybody see that? all the directions on those little greater than, less than's really matter. This is where you're going to think I'm a mean teacher. You'll think I'm nice when you add wrong and I go ahead and give you all the points or maybe just one off, even though you got the wrong answer. Then you'll think I'm mean when and you just turn one of those little symbols the other way. I'll probably give you a straight 0 on one of these problems, because that's everything. That is the concept. That's not small. The whole concept is which way those things go. That's the whole thing on this. So really don't look at that as a small detail that's irrelevant. That is the problem. Do you know which way those things go, right? That's really, really important. And the fact that that's a triple, the lesser always a triple, and the greater it's got two separate. They got a greater amount, right? On that. Questions on that? Set up from there? Yeah.
So the greater will always have both the less and the positive, or
The greater will always have the 2 with the or. We'll have a greater number. Yeah. That's right. Then you just solve it. Solve it from there. Good. So the first step is everything. Notice the absolute values have been removed in both cases. All right. All right. So is this thing a function? So there may be a couple multiple choice on this test we're taking. A couple like function, not function, or odd or even in a minute. All right. So is that a function? How do you know if that thing's a function? This one is a function. It's only not a function when you have something like, say, 2, 3 and 2, 1, right? When same x to 2 different y's. That's the big no-no, right? If you have the same x going to 2 different y's, that would be the big no-no. We don't have that here. No problem. It doesn't have that problem. Whoops, the little thing's not working here. Come on. No problems. So that one's a function. All right, next. Find the point in the graph that is closest. That word, remember I talked about the superlatives, right? Close, closer, closest, right? So whenever they use the superlative, the est at the end, the est, something's got to reach out and grab a hold of it. You got to think, oh wait a minute, what is that? What did Mr. Hart say about that? We do the est, the biggest, the smallest, the closest, the furthest, the tallest, the whatever, right? What does that always mean we're going to do? That's finding what closest means minimum distance. That's what it means to be closest. You're at the minimum possible distance, which means we're going to have to use our calculator, right? We're going to eventually use the graphing. We're on part 2 now, where you can use the graphing calculator. Use the graphing calculator, and you're going to graph something like that, and you're going to find the minimum. Remember those? That's what we did in the last section, 2.6 that we just finished. This is a 2.6 problem, right? These are the kind where you write the distance formula, square root of x1 minus x2 squared plus y1 minus y2 squared. Remember those? And what are your 2 points? 1, 0, and xy, right? They gave me 1, 0, and the other one's just a general xy. So you put those into the distance formula, 1 minus x squared plus 0 minus y. Doesn't matter what order you put them in. So the distance formula, foil that out, you're going to get 1 minus 2x plus x squared. The other one's just going to be y squared. Good to there. Now there's only one problem. I can't quite type that into my graphing calculator because I have a y. This y is a problem. You can't type y into your graphing calculator. So what do? Substitute right there, plug it in, right? Plug in y is the root of x. So go, okay, so I've got 1 minus 2x plus x squared plus root of x. That y squared becomes root of x squared because y is the root of x, huh? And then that's what? 1 minus 2x plus x squared plus x. And so then combine like terms, minus 2x plus x is minus x.
I have a
Question?
question. Isn't the distance formula supposed to be x2 minus x1, y2 minus y1?
It doesn't matter. Yeah. Yeah, because, good question. The question is, shouldn't we have it the other way? The order, because it's squared, the order of subtraction doesn't matter. Think about if you subtract 2 numbers. 5 minus 3 and 3 minus 5. What's the difference between those two? One's a positive 2, one's a negative 2, right? So that does matter, but if I square them both, 4 either way. So it doesn't matter what order. It does in the slope formula because those aren't squared with the y2, y1. But with the distance formula, it doesn't matter because they're squared. Good question. So we got all that then, and now we just type that into our calculator, right? We just go y1 equals that thing, and graph it and find the minimum, like I showed you right here. All right, so I did all that yesterday. If you're having trouble, I'll be glad to help you. Office hours, come on in, get the help you need, or even right after class. I have a few minutes. I'm going to go on to number 3. I don't have room. So there it is. I'll do it in the next sheet. Find the domain of y equals square root of 13 minus x. Okay. Y equals square root of 13 minus x. Was that number 3? Whoops, what just happened? Domain. All right, remember for domain we had 2 issues. Number 1, if you have any denominators, you say denominator you cannot equal 0 and you solve. Number 2, if you have a square root, the inside of it, you take the inside out, and you say inside you cannot be negative, meaning you must be greater than or equal to 0. Not negative. Not less than 0. So greater than or equal to 0. So that's what we have here. We have the inside of a root. So we say, remember, we're looking for trouble spots, right? Domain is asking what can you plug in. That's my whole, you can't put knives in the toaster thing, right? There's certain things you shouldn't plug into certain other things. You shouldn't put negatives in roots. So we say, all right, inside, you better be greater than or equal to 0. We can't let you be negative. So then we solve that. How do you solve that? Subtract 13. Divide by -1 and flip the symbol, right? When you divide by a negative, must flip the symbol. So that's positive 13. That's your answer. X must be a number 13 or less. And that makes sense if you go back up to the original, right? If we put in 13, that'll be 13 minus 13 is 0. Square root of 0 is fine. If you do less than 13, that's okay also. Like it said, less. 12 is fine. 13 minus 12 would be 1. Square root of 1 is fine. But if you do more, like put in 14 for x, that would be a problem, wouldn't it? Because that'd be -1. You can't take the square root of negative numbers. That's imaginary. That's why the acceptable inputs are numbers 13 or below. Good? Tim?
Sorry, this is the last question. But once you get the minimum and the distance
Right.
is a y value.
Oh, yeah.
But in order to find the y value that correlates with the x coordinate minimum that you got, would you plug it into the original equation?
Yeah, okay, so what was that function? It was y1 equals, this is number 2, was it number 2?
Yeah.
2, and what was it? y1 equals?
1 minus x plus x squared.
Yeah, just that. Okay, yeah, so then you graph it, and when you graph it, you get some kind of thinger, and you get a minimum, and that minimum, isn't it like 0.5 and 0.866?
Yeah.
I was just looking at it. All right, so so good point, Tim. So that is x and distance. Remember me making a big deal out of that yesterday in 2.6? Saying it's not x and y, it's x and distance. Why? Because what is this y1? It's the distance formula, huh? So when you first get your answer on your graph and your minimum, you're getting x and distance. And I asked you in that question for x and y. Well, how do we get y then? If this is x and this is not y, it's really distance because it represented the distance function. Well, then how do you get the normal y on the graph? Go back to the equation. Y was equal to the root of x. So if you have x, plug it in. Y is the root of 0.5, which is, I don't know, what is that, 0.71 or something?
0.707.
Yeah, 0.707. That's your y value. So the answer to the question, the xy, is 0.5, 0.707. The 866 was the distance. I might ask you for any of those. I don't even know. I made the exam up, photocopied it a while ago. I don't know what's on there. But I might ask you for x and y. I might ask you for x and distance. Just know what all of them are. Yeah, good question. Let's do this one. Okay, so remember the even-odd test? So for even-odd, I gave you a test. I said step 1, plug in negative x. Step 2, so let's do that. Let's do number 4 here. So -4, negative x, over absolute value, negative x. So I just plugged in negative x for x. Step 2, simplify. So clean it up. So how does that simplify? Well, 2 negatives make positive. Absolute value negative vanishes, right? Not good. Step 3, now you compare the new one to the original. Well, let's just do it this way. let me just say compare, and there's three cases. Case 1, the new is equal to the original. They're identical. What does that mean if they're identical? What kind of function is it? Even, odd, or neither? Even. Case 2, if the new equals -1 times the original, then it's odd. And then if neither of those is the case, it's neither even nor odd. Not every function is even or odd. Most are neither, really. Okay, so there's the test. So I plug -x in, I clean it up, and I say, how does that compare? Here's the original. So here's the new, here's the original. How does the new compare to the original? Here's the new, the original, it's been multiplied by -1, hasn't it? So it's odd. So it's odd. Everybody see that? That one's odd. Because the new, after plugging in -x and simplifying, the new compared to the original is times -1. So that's odd. How about number 5 down here? Number 5, take the original, cube root of 5x squared, plug in -x, and then clean it up, cube root of -x squared. Well, that's just, negative squared vanishes. So there's the new. How does that compare to the original? It's the same as the original, isn't it? So that means even. So this one's an even function. Remember that? All right, so number 6, let's go to, 4x squared minus 5y equals 68. 4x squared minus 5y is 68. What number was that? Number 6. So number 6. It says you can use the graphing calculator, find the intercepts. So if you want to use the graphing calculator on this thing, you've got to get y alone, huh? So let me jump the 4x squared over there. Becomes a negative 4x squared, right? When things jump to the other side, they switch the sign in front of them. Divide by the -5. Boom. So y's alone, minus 4x squared plus 68 over -5. So you got to get y alone because your graphing calculator requires you to, right? What's on the graphing calculator? Yeah, y1 equals. So you got to have y alone, huh? That's just how the graph calculator is set up. So get y alone. Now, let me give you a big caution. A lot of people generally know that, but they're not skilled with using the graphing calculator. They will type this in. I see this a lot. That won't work. What's wrong with typing y1 equals that right there? That's a divide symbol there. Anyway, why is that not right? What do I need to do to fix it? How do I fix it? You must put parentheses around that. Otherwise, it's only going to divide the 68 by 5. It doesn't know the minus 4x squared plus 68. The whole thing is divided by the -5. It doesn't know that unless you put parentheses. So remember, whenever you use your graphing calculator, when there's more than one item added or subtracted, if you got adding or subtracting, let me say it that way. If you've got adding or subtracting in a numerator, a denominator, or a power zone, you've got to put parentheses around that. Otherwise, the calculator will not realize that. Well, yeah, it's not just adding, subtracting. It's more than one item. Yeah, I'm going to stay with my original mantra because that's what's true. More than one item. If you've got more than one thing in a numerator, denominator, or power zone, you've got to parenthesize it, or the calculator won't know. Yeah, so type that into y1 and graph. You'll get some kind of graph. I think it looks like that. Find those 3 intercepts. These are called roots, or they're also called zeros on some calculators. And this is this one is let the value. You can go to the table. Go to the table. Just hit the table button, and you'll find the value when x is 0, y is negative something or other on that by just going to the table. Remember, hit second table, and you can find that on the graphing calculator. You could also do that one by hand by plugging in x0, solve for y, y0, solve for x, right? You can find intercepts by hand that way also. So, what just happened? I'm confused. There. All right, so here we go. So this one, I'm just going to say y1, y2, graphing calculator. Let one side be y1, one side be y2, and do the intersect thing. Find the intersect. I think you get like 4 answers. So do the intersect thing on your graphing calculator. Find this. If you have trouble with that, come see me. I sent you some YouTubes as well for how to do those to everybody's email. So if you're having trouble with that, look back on your emails I sent you. Let's do this second part. Now this is for sure on the exam. Remember, this was a promise. It was a promise that the difference quotient will be on the exam tomorrow, because that's the first thing you're going to do in Calculus 1. Right off the bat, you'll start using the difference quotient. So I want you guys to be pros right off the bat. So how do we do it? So f of x plus h minus f of x all over h. So let's plug in x plus h to that function. X plus h squared plus 3x plus h minus 6. Everybody good to there? That's f of x plus h minus, and then f of x all over h. Everybody see what it did? So this is f of x. This all is f of x plus h. Good? Like that? Then you just got to do a bunch of messy algebra. Yeah, I'm just going to go dot, dot, dot. Just crank out the algebra on that. Yeah, so I've done a couple of those other ones. Glad to help you. Remember, the first step is x squared plus 2xh plus h squared, right? You got to FOIL that out. And then 3x plus h, no, 3h, right? Plus 3h minus 6 minus x, and this distributes, minus 3x plus 6 all over. Remember I said that all the non-h'ers, non-h terms cancel. They always cancel. So this should cancel. It doesn't have an h. It better cancel. Sure enough. Now this doesn't have an h. It better cancel. Sure enough. This doesn't have an h. Better cancel. Sure enough. It's a good double check on your algebra. All the items in the top that don't have an h, when you're doing the difference quotient, remember that. If your Calc 1 teacher forgets to mention it, they always cancel out. All the non-h'ers when you're doing the difference quotient. The rest, gather like terms, cancel, blah, blah, blah. All right. Okay, so remember I gave you a simple rule. These should be free points for you. If you remember the rule, if you have it on your 3x5 card, it's well, let me say what it's not a function. Remember I gave you a simple rule. It's not a function if, we've had various, we had the, 1x leads to 2y, or 2x's go to the same y. But how do you test for an equation? It's not a function if y to some even power or plus or minus anywhere. Otherwise, it is a function. Remember that? You guys never forget anything I say in here, right? Listen to my tapes and watch my YouTubes day and night, right? All right, so yeah, that's all you got to do. Is just check. So look at number 11. It's got a y squared. No, not a function. That'll wreck it. So that's a problem. Not a function. How about number 12? Has it got y squared anywhere? No. Has it got plus or minus anywhere? No. It's good. Those are free points, right? Just know that rule. All right, last one. Even, odd, or neither by looking at a graph. How do you decide even, odd, or neither? By looking at a picture. Remember, even is y-axis symmetry, kind of like y equals x squared. That's what we call it even, because it's even-powered kind of thing. Right, y-axis symmetry. Odd, what's odd? Well, that's origin symmetry. Remember, what's origin? 180-degree rotation, halfway around. So, right, that'd be like if you had something there and something there, right? But we're used, that's true, what I just wrote. Also, x cubed, which we're used to, right? That's why we call it odd, because it's like the odd-powered x cubed, right? Halfway around, it's the same. Well, what about this one? Yeah, it's odd. Halfway around, it's the same, isn't it? If you grab that thing and turned it halfway, or turned your paper halfway around, it would look like you hadn't turned it at all. It'd go right back onto itself, wouldn't it? That's an odd function. All right, we did it. I mean, I don't do roll, but I never do roll. So we made it through the review. All right, so